Hey, good morning. This is Mr. Willis, and today we are going to be working through a lab called the Beanium lab, and it is a representation of how various isotopes are measured in order to create a value for the average atomic mass. All right, so let's get started. The first thing we're going to do, we have a cup full of beans, and this represents one element, but each bean represents a different type of isotope. And remember, that's going to have the same number of protons, but a different number of neutrons, and so it's going to be have a different atomic mass, even though it has the same atomic number. And so we're going to first take this element, and we're going to count the number of atoms of each isotope. So let's go ahead and get started. And we'll begin to sort these out. All right, and so we have sorted and counted each of our beans. We have our navy beans, and there were 50 of them. We have our pinto beans, and there were 233 of them. We have our black beans, and there were 17 of them. And we have our red beans, kidney beans, and there are 51 of them. Now, step number 2 says to calculate the average mass of one atom of each isotope. So for instance, we need to count the average mass of one of these black beans. To do that, we will mass all of them, or a large number of them, and then take the total mass and divide by how many there are. So let's do that real quickly. All right, so we have placed our 17 black beans in the pan. We would never do this with a chemical, but since it is just beans and we cleaned our pan just before measuring, and we are not going to eat these, it is all right for us to place them directly in the pan. And so now we will take that and we will mass those. And I'm just going to see if we can do that real quickly. Oh, there is the bell. Go on to your next period class, and we will, no. All right, and so that is going to be very close for us. I'm going to tap that back just a little. All right, and so the final value for the black beans appears to be 3.622. This time we've placed the 50 navy beans in the pan, and if you look, it appears that our riders are in the 20 position, the 2 position, and let's see, right there, we will let you read and make your judgment about where that last one is. This time we've placed the 51 kidney beans on the scale, and you can see that we're in the 20 slot, the 2 slot, and then we'll let you make your reading for the last rider. And now we have our 233 pinto beans in the pan, and we are on the 70, the 8, and our last rider right there. So now we need to calculate the average mass of one of our isotopes. And so, for example, the 17 black beans had a mass of 3.622 grams, and 17 beans. And so when we take that and do our division, I will do that here. 3.622 divided by our 17 beans, and we find that we have 0.2130 grams per bean, and we'll put that at 4 significant figures. So 0.2131 grams per bean. 0.2131 grams per bean. And that was actually our black beans, so I will include that. All right, that is how you calculate those average mass for each isotope. So go ahead and do that for the remaining 3 types. All right, the next step says that we need to calculate the percentage of each isotope in the Beanium sample. So what we'll need to do for a percentage is we need to know the part that each isotope is divided by the whole amount of the sample. Now, when we take our numbers, which were 17, 50, 51, and 233, and add those up, you see that that totals to 351. And so for each percentage, our whole will always be 351. And in this case, the part that the black beans made up were 17 beans. So I'm going to put 17 divided by 351, and then multiply by 100. Oh, look at that. My calculator kept it as a fraction. If I push Control Enter, it will actually force it into a decimal. And we can see that it's 0.0484, again, at 4 significant figures. And so by multiplying that by 100, we get, let's see, 4.843% for the black beans. All right, go ahead and continue that for the other 3. Someone just asked an interesting question. They said, why, when originally you had 17, that only has 2 significant figures, why are you using 4 significant figures in your answer? Well, this was exactly 17 items. And so it is not 17. It is, since it is an exact number, it is actually an infinite number of significant figures. And the same with 351. We do not need to put an infinite number of significant figures here, so I was maintaining our use of 4 from our original measurement. So thank you very much for that question. I hope that is clarifying. All right. Question 4, or step 4, says to calculate the average atomic mass of Beanium. The way that the average atomic mass is calculated is that you take the percentage of isotope number 1 and you multiply by the average mass of isotope number 1, and then you take that value and you will add that with that same calculation for isotope number 2, isotope number 3, and so on and so on. In our case, there were 4 isotopes, so there will still be a 4th bracket set of calculations. Then we will sum those up, and that should give us the average atomic mass of Beanium. All right, and then there will be some analysis questions for you to answer as well. Thank you so much for following along and participating with us in the Beanium Lab. I hope you're having a great day. Thank you.